The objective of this video clip is to demonstrate how you might design a composite part to give you better performance than, say, a metallic part. And I chose an example here using an aerospace vehicle. Often we have target vehicles that have interstage adapters similar to the picture you see here. And inside these interstage adapters that join the stages are bulkheads. And on these bulkheads we attach electrical components, and it's very typical for us to attach guidance systems to these bulkheads on the internal side of these ISAs or interstage adapters. One thing that bulkheads always have is a characteristic natural frequency, and we have to be very careful that the natural frequency of those bulkheads do not correspond with either the nozzle frequency of the rocket or the natural frequency of the rocket itself. And that typically results in a stay-out zone or stay-out frequency of about 80 hertz and below. So we need to design bulkheads that have frequencies at or above 80 hertz. So if I start out with say a target vehicle where we actually would want a heavy bulkhead, like maybe use a piece of steel or aluminum to keep the vehicle slow enough or low enough to perform its objective, we'll start with an idea like that and see if we can design an aluminum bulkhead with a frequency of 80 hertz or above. And then we'll assume that this vehicle is now going to be chartered to go into space, and we'll need a lighter bulkhead. So first thing we need to do is to define a laminate. So new laminate. I'm going to add a single ply here, and since it's aluminum, it's going to be very easy to identify. So I'll just assume maybe this is made out of 6061 T6 aluminum. I'm going to call this the aluminum bulkhead. The thickness here, I'll start with, say, 1.75 inches thick, assuming that this was originally a target and they wanted a nice heavy bulkhead, an angle 0. And I'll save it. Now with that done, we can go over here to the plate and look at the vibration response of this. So remember, we wanted to stay above 80 hertz. My aluminum bulkhead. I'll go over to my plate geometry, and let's assume that the width of this, we can assume that certainly the bulkhead would be circular, but it would be close enough for our purposes to start the design with an approximation using a square plate. So I'll say it was about a 60 inch by 60 inch plate, representing an approximate 60 inch diameter. And we could choose simply supported or clamped. A lot of times it seems like most of the bulkheads have a minimum number of bolts around it. Even though it's clamped down to a ring, it's it's approximated best by simply supported. So let's see what that frequency is. It turns out, well, we got lucky on this. The natural frequency is 92 hertz, so that is above our stay-out frequency, and we're successful there. So let's remember that 92 hertz. And now let's say that we've been chartered now to send this into space. Now we've got to build a bulkhead that has been optimized to give us the same frequency, but hopefully we can save a lot of weight. Now I'm going to do some math in the background here. If I have 60 by 60 by 1.6 inches or 1.75 inches thick by a density 0.1, our first bulkhead would weigh 630 pounds. So 630 pounds, we'd like to get that down to under 50 pounds if we could. So let's build another laminate here. And let's go ahead and start with a layup sequence. And I'm just going to use any kind of carbon epoxy here that comes to mind. Let's use, for example, the IM7 8552. We'll assume that the thickness for these plies is, say, 5 thousandths. I'll start out with 0 degree ply, and to accelerate our time here, I'll repeat this. Let's say we'll make it quasi-isotropic with 6 plies on the top face sheet. Use a sequence of 30 minus 30. We'll say 60, and then minus 60, followed by a final inside ply of 90. And now let's add a core ply. Now I've taken the liberty of setting up a core ply in here underneath my lamina because it just makes it a lot easier. You can go into your core section here and do the same kind of things if you want. I find it easier to build it directly inside the lamina sequence. So here's my core ply. And let's start with, say, a 0.75 inch thick core. I'm doing this for a reason, because I'm going to select the whole series here, and I'm going to call it symmetric. So I end up basically with 1.5 inches of core, which is very close to the 1.75 inch thick that we used on the original one. And we'll assign it with 0 degree on the core. It doesn't really matter. So let's call this the equivalent bulkhead, let's say. We'll save that. So we should now have the equivalent bulkhead under our laminate tree. We do indeed. We'll go back to our plate vibration calculator. We'll open up the equivalent bulkhead. I believe our original geometry was 60 inches by 60 inches. Our thickness is very close to our original design at 1.56. That's good. And looking at simply supported, let's see what we get. We got 92 hertz. If that wasn't enough, let's say we had to get to 95 for whatever reason, we could, of course, always go back. And remember, our original was 1.75 inches thick. We might opt here, for example, to go, say, 0.8 inches, because that would still be within the original dimension. I can go back and calculate. And sure enough, now I get 97 hertz. So there are ways we can iterate on that. So a very quick example to see that how you can use CompositePro to devise a composite structure that is optimized, or better than a metallic part. In the background here, I'm also doing some math on these face sheets. Turns out the face sheet weight on this would be 13 pounds, and the core width 26.5 pounds, for a total of 39.5 pounds. So going from 630 down to 39.5 is certainly an increase in performance.